Hey everyone, Miss Butler here. I have a video for you on covalent bonding and then specifically how to draw Lewis structures for covalent chemicals. So we're going to review what we saw in the last video, the difference between ionic and covalent structures and figuring out which one's ionic and what's covalent. We're going to focus on writing the names of covalent compounds and the formulas of covalent compounds. And then we're going to do Lewis dot structures to show chemical bonds, those covalent bonds, and those bonds will represent shared electrons. So those are kind of our three main goals. So just a reminder, an ionic bond is when we have two different things and one gives away electrons and the other takes electrons, whereas covalent bonding happens when two atoms are going to share their electrons between the two elements. Everybody wants to have a full octet, a full outer shell of valence electrons, and there's just different choices in how to do that. Is it I'm giving and you're taking, or can we share some electrons so we both have a full outer ring? So this entire unit is about covalent bonding. So remember, a covalent bond is going to form when two elements share their valence electrons, and those shared electrons become part of the full outer shell for both atoms. And a good vocab word is a complete octet or a full octet. So when both atoms are sharing their electrons, those shared electrons are part of both elements, making them all feel like they have a complete octet or 8 valence electrons. The types of elements that are going to form covalent bonds are nonmetals with other nonmetals. And just a friendly reminder, the word molecule or molecular compound refers to two or more atoms that are bonded covalently. So really when I say is it covalent or molecular, I'm saying the same exact thing. So a molecular compound is covalent. So let's say I have some covalently bonded compounds or molecular structures. What are some maybe properties we would see, or what would these different structures or chemicals look like? Well, the kind of tricky part is we can have chemicals that are covalently bonded, and they could be gases, like oxygen in the air. They could be liquids, like H2O, or they could be in the solid form. So we have lots of different examples of covalently bonded compounds. Typically, though, they will have lower melting points and boiling points compared to ionic. So if I'm comparing two things, one's ionic, one's covalent, the covalent thing will melt at a lower temperature and boil at a lower temperature compared to the ionic one. They don't usually dissolve well in water, and they do not usually conduct electricity, so we're not able to transport that electric current through the substance. So again, there are a few exceptions, but these are kind of the norms of properties you can expect if you have a chemical that is covalently bonded. So the quick test we're going to do to see if something is ionic or covalent is by looking at the periodic table. If you have a metal, one of these purple ones, bonded with a nonmetal, one of these green ones, it's going to be ionic. If you have two nonmetals, so two green ones, and that includes hydrogen, he's a nonmetal, bonded together, then it is going to be covalent. So I would like you to try these. We've seen this in the last video, but you're literally just going to tell me, is it ionic or is it molecular, same as covalent, right? Molecular means covalent. So next to each one of these, and you can use the idea about metal with nonmetal is ionic, two nonmetals are molecular. And then don't forget, if we have lots of capital letters, those are polyatomic ions, so that's going to be something that's ionic. Okay, so pause the video. I will put the answers up for you to check in 3, 2, 1. All right, hopefully any that had a metal with a nonmetal you labeled as ionic, or any with multiple capital letters, so I would say more than 2 capital letters, those are ionic. The ones that only have 2 capital letters and both are nonmetal, carbon and hydrogen, hydrogen and oxygen, those ones, or xenon and chlorine, those ones are going to be molecular or covalent. All right, so let's say we have now decided that a chemical is covalent or molecular. So we have maybe a list and they say, is it ionic or covalent? And we say it is covalent. Well, there's a way then we can name a covalent chemical, and these probably sound really familiar to you. But there's kind of a general format we're going to use, and that format is prefix, name, drop the ending "ide." So prefix, name, "ide." Okay? And so that's going to be the structure we use just for covalent chemicals. And this whole unit is covalent, but it's always good to double check, do I have two nonmetals? If so, I'm going to put a prefix with the element name, then a prefix with the element name, drop that ending and add "-ide." I'll show you some examples. Before we get into the examples, let's talk about the prefixes. So we are going to put prefixes that represent how many of that element there are in the chemical formula. So if there's only one of that element, we're going to say mono. If there's two, di. 3 is tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa, like octagon. N is nona. And 10 is deca. So these are something I need you guys to memorize, but a lot of them, right? Tri is 3, penta, think of the Pentagon in Washington, D.C. A lot of these should be pretty obvious to you, but it will take some practice and maybe some flashcards to help. So these are the prefixes that we're going to use, and let's look at some examples now. All right, let's practice. So we're going to use this format, prefix name, "-ide, to help us out. So first one, I see that we have 2, so this 2 applies to that symbol that it's behind. We've seen that before when we learned particle drawings. So that 2 applies to the H, so we need to use our prefix for 2, which is di, and our element name is hydrogen. And now we move on to the next one. Well, there's no number right here, and when there's no number, it's an imaginary 1, because really, the element symbol itself is the representation of that 1. I just have 1 oxygen. And then if we have any more than 1, like 2, 3, 4, all the way up to 10, we would have a number there. So there's 1, and the prefix for 1 is mono. And we need to have this element name, which is oxygen. But what we're going to do is we're going to drop the ending and add "-ide. So this is going to be monoxide. So this is dihydrogen monoxide. I didn't put an extra O just because of convention. It gets kind of messy, but I would not mark you wrong if you said monooxide, all one word, with that extra O. But we tend to drop double vowels just because it sounds better in the English language. But anyways, this is called dihydrogen monoxide. That is the formal chemical name for H2O, which is water. Let's try this one. I have 2 of this element here, so we put the prefix for 2, di, and that element is nitrogen. So there's my prefix name, and now we're going to do prefix name "-ide. So I see another 2. This is going to be di, and then we saw oxygen turned into oxide. So dinitrogen dioxide is N2O2. Another thing I want you to add to your rules. Let's look here. We have CO2. That is called carbon dioxide. CO is called carbon monoxide. I noticed, though, that both of these, we said the format is prefix name with the "-ide, prefix name with the "-ide ending. I noticed that these ones don't have prefixes on the first element. So this is a rule that you should write down. We do not need to use mono as the prefix if it is the first element. So if the first element only has 1, like this and this, we do not put a prefix on the first one. But if the second element has 1, we will use mono as our prefix. So this one, instead of just carbon oxide, is carbon monoxide because we put that prefix on the oxygen. Okay, you are allowed to put prefixes on the first element unless it's mono, then you skip the prefix. Hopefully that makes sense. So there are 7 special molecules called the diatomic molecules that are covalently bonded. So normally we look for 2 nonmetals bonded together, right? And it doesn't matter what the subscripts are. I'm just looking at the 2 capital letters. Are they both nonmetals? That's what makes it covalent. But there are 7 diatomic elements that bond together covalently. So this is H2. That means the hydrogen is covalently bonding or sharing electrons with the other hydrogen. Bromine, 2 bromines sharing electrons together. So these are the 7: hydrogen, bromine, oxygen, nitrogen, chlorine, iodine, and fluorine. And I need you to recognize those, and I need you to know that they're covalent. And I also will ask you to draw them sometimes. Okay, don't worry about naming them. Honestly, we'll just call it hydrogen, bromine, things like that. But you will need to recognize those as covalently bonded structures. Here's how I remember it. Okay, I use this phrase. Hike bro, need Cliff Bar. So hydrogen is the H. Hike bro, my bro is the bromine and the oxygen. Well, if we're gonna go for a hike, we need, that's the nitrogen. Cl is chlorine. F is, so iodine and fluorine. And then I just added a bar. So hike bro, need cliff. Well, I guess I could say I'm going to go for a hike. I need to climb a cliff, right? Hike bro, need cliff to climb. But I'm more not really the type of person who's going to climb a cliff. I'm the type of person, if I'm going for a hike, I'm going to take a peanut butter Cliff Bar. So that's how I remember it. Hike bro, need Cliff Bar. And so those 7 from this phrase, H, B, R, O, N, C, L, I, and F, those are the ones that are the 7 diatomic elements. They covalently bond with themselves. Okay, next we're going to draw Lewis structures, and these Lewis structures are going to have chemical bonds in them. So they're not single elements, and hopefully some of these will look familiar from what you've seen in maybe some other science classes. But here are the steps, so make sure you write these down. Step 1, we need to count up the number of valence electrons using our periodic table. We're going to arrange the elements. We're going to connect the elements with single bonds. And then we're going to fill the outer, and then we'll fill the inner, and I will explain what that means once we get there. So write down those 5 steps. All right, so I already have the answer up on the screen. This is what our final product is going to look like for H2O. And so I want to draw it with you guys, and the end goal, it would be that we actually match this correct answer. So step 1 was to count up the valence electrons in this molecule. Well, we are going to use our periodic table, and remember the columns have the number of valence electrons. So hydrogen is in the very first column or group, so that means each hydrogen has 1 valence electron. And so because there's 2 of them, that's going to equal 2 valence electrons from the hydrogen, right? 2 valence electrons each. So, 1 valence electrons each, and there's 2 hydrogens because of this 2. So we have 2 from the hydrogen. Oxygen, we keep counting over in our columns. Remember, we skip the transition metals in the middle, so find boron. Boron is in the 3rd column that we're going to count, and so that's 3, and we just keep counting over, and you should find that oxygen is in a column with 6 valence electrons. So if we add those together, 2 plus 6 equals 8 total electrons. We're only going to count the valence electrons because those are the ones that are going to bond, okay? So we have our piggy bank, 8 total in the piggy bank. The next rule of thumb is to arrange the elements. Here's how we're going to arrange them. If you ever have an element by itself, just one of them, that's going to go in the middle. So I'm going to put oxygen in the middle, and then you're going to put the other elements just kind of around it. So I could have put one here, that's fine too, not a big deal. If there's more than 2, right, we could do one on each side. Great. So here's what we're going to do. We are now that we've arranged the elements, we are going to connect those elements to the center one only using single bonds. So here's how it works. I want you to picture connect the dots. So if you ever played connect the dots as a kid, you literally just draw lines in between the numbered dots. Okay, and here's how those dots work. In each bond, there are 2 electrons, one right here in that dot and one in this dot, okay? So there are 2 electrons here and there are 2 electrons here, and they belong to both the hydrogen and the oxygen. So right now, I have used up 4, right? 1, 2, 3, 4. So in my piggy bank, I have 4 electrons left to work with. Then it says in my directions to fill the outer. So what we're going to do is we are going to put dots on these outer elements until they are satisfied. Every element wants 8 electrons except for hydrogen and helium are happy with 2. Well, hydrogen already has 2 because remember this green line represents 2. These both belong to hydrogen and they both belong to oxygen. This hydrogen is also happy because it has those 2 electrons in the bond, right? These 2 belong to this hydrogen and they also belong to the oxygen. They're being shared. So we're going to skip step 4 because this hydrogen is satisfied and so is this one. Step 5 says to fill the inner. So whatever is left over on my list, I have 4 electrons. I'm going to put 4 dots around oxygen, and typically we draw them in pairs, okay? These guys are called lone pairs. So those are electrons that only belong to oxygen. So this is a lonely pair of electrons, and this is a lone pair. That means they only belong to the oxygen. And because we put those lone pairs, we put 4 dots. We used up 4, so now we have 0 electrons in our piggy bank. We are done. As you can see, my angles are a little bit different, and where the dots are different than this overall picture, but that's okay. They're still paired up, like that's a pair, and the overall general form is the same, so we are correct. All right, let's try these. First step, count up the valence electrons. Nitrogen, that whole column will have 5. Hydrogen always has 1, but there are 3 hydrogens. So when we add them together, there are 8 total valence electrons, just like we had with oxygen. Now we arrange the elements. There's 1 nitrogen and 3 hydrogens, so I'm going to put nitrogen in the middle and the 3 hydrogens around it. Again, if you put 1 hydrogen up top, that is okay. Next step is to connect them with single bonds. So remember, in a bond, there are 2 electrons, 2 electrons. Whoop, that's a short one. So 2, 4, 6. So I've used up 6. So right now we have 2 electrons left in our piggy bank. We're going to fill the outer. Well, hydrogen, we said last time, is satisfied with those 2 electrons in the bond. So this problem, similar to the H2O, we don't need to fill the outer. That means we're going to use these last 2 electrons to fill the inner right here. And so we used up 2. We have none left in our piggy bank. So there is our structure. We have 3 single bonds, and then nitrogen has a lone pair of electrons. Let's look at this one. Carbon is in a group that has 4 electrons. Hydrogen has 1, but there's 2, and oxygen has 6. So I add up 4 plus 2 plus 6. That gives me 12 total electrons that I can have in my picture. Okay, this one has a lot going on. Okay, so I'm going to give you a little hint, and don't stress about figuring this out on your own. I'm going to put carbon in the middle, and I'm going to put oxygen and then hydrogen. So everything's just going to bond to that center carbon. And my clue, even though there were 2 things that only had 1, was that when that happens, I usually pick the one that's first in the formula to be my center element. Anyways, we're going to connect with single bonds. So I put a single bond here, I put a single bond here, and I put a single bond here. So that used 2, 4, 6 electrons, right? 2 in each bond. So that means I have 6 electrons now. I'm going to move it over here in my piggy bank. Okay, now we fill the outer. Well, remember, this hydrogen is satisfied because he has these 2. He has these 2. Oxygen is not one of my elements, hydrogen or helium, that only wants 2. Oxygen actually wants it wants 8 electrons total. So it has 2. So I need to fill the outer. There's 2 more. And now oxygen is happy because he has 2, 4, 6, and the bond right here makes 8 electrons, and that's what oxygen wants. We used all 6, so we have 0 left in our piggy bank. We have a little problem though, because the last step is to fill the inner, and carbon only has 2, 4, 6 electrons. And carbon also wants 8 like oxygen. So we need some extra sharing to happen. So I'm only going to do this as a last resort if my piggy bank is empty and my middle element is not satisfied. What we're going to do is we're going to take those two and we're going to make an extra bond. So what will end up happening is those 2 electrons are going to move, and I'm going to have a shape like this. Try to keep all the same colors. Bond, bond, bond. And those 2 electrons that I just moved are going to be in a bond like this. So we call this a double bond. So there's 2, 4 on oxygen in the blue. The green has now 6, the red has 8. So this oxygen has 8, carbon has 2, 4, 6, and the red makes 8. Now everybody's happy, and I didn't mess with my piggy bank because all I did was move these to be shared. So let's just kind of talk through some strategy here. Here's the chemical or the Lewis structure we got for NH3. And so in this situation, we had extra electrons in our piggy bank. We're going to put them on the element in the center, right? So that middle element has a lone pair. Here's our final structure, Lewis structure that we got for the CH2O. If we need more electrons, because our middle element is not satisfied, then we will do a double bond like we have here, or there is such thing as a triple bond. Please note that this is rare. We're only going to do this if we have to because our piggy bank is empty and our middle element is not satisfied. So one more time, you should add this to your notes, maybe underneath the steps. If we have extra electrons, put them on the center element as lone pairs. If you need extra electrons because your piggy bank is empty, then we will do double bonds or triple bonds. But we only do that if we need more electrons than we have in our piggy bank. All right, let's try this guy, see if we can do it. Sulfur has 6 valence. Fluorine has 7 times 6. Let's see if I can do some math. Okay, so we get our grand total of 48. Somebody check me on that in my piggy bank. So we start, there's only 1 sulfur, and I'm going to put 6 fluorines all around the sulfur. And now everybody gets to sync, so that's step 2, right? First, valence electrons. Second step, arrange the elements. Step 3 is to do a single bond between each element and this center atom. Don't do any weird wagon wheel stuff. We just do 1 bond between each outer element and the one in the middle. Okay, so let's see how many we use there. Remember, each green line has 2 electrons. 2, 4, 6, 8, 10, 12. So we got to subtract 12. That gives us 36 now in our piggy bank. Now let's fill the outer. Everybody wants 8. So right now, each fluorine needs 6 more dots. So 3 lone pairs, like 3 pairs of shoes. That's 6 total shoes. And we'll double check by counting up once I'm done. Okay, so 2, 4, 6, and the green bond is 8. 2, 4, 6, 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 the green bond is 8. If you check me, we use 36 electrons for those dots, so our piggy bank is at 0. Now, normally we fill the inner. Let's check, does my inner have 8? 2, 4, 6, 8, 10, 12. Well, that's not good because sulfur only wants 8. So we should probably talk about what this means when our center atom has more than the maximum 8. Here's that structure one more time. Sulfur has what's called an expanded octet. So if you have an element that's in the 3rd row or lower, which sulfur is in the 3rd row, so the 3rd row of the periodic table or lower, you can have more than 8 electrons. Okay, I like to think of this as taking one for the team. Sulfur will take the extra electrons, 2, 4, 6, 8, 10, 12, as long as everybody else is perfect. So all those fluorines are perfect, happy with 8. Sulfur will take one for his friends, take one for the team, and have more. As long as that middle element is in the 3rd row or bigger, it can do that. Okay, it doesn't want to, but it'll do it for its buddies. Okay, and then the other note is only the one in the middle can do this. The fluorine out here, he can't expand. Only the central atom in the middle can take one for the team and have more than 8, and he has to be an element that's in the 3rd row or lower down on the periodic table. It just means he's big enough to do this. Okay, so let's make sure you add that to your notes. Maybe as an additional rule, you can add it up to where we talked about double bonds and putting extra on the central atom. So if an element is in the 3rd row or further down, you can have more than 8 electrons. It's called the expanded octet. Only the central atom can do that. And again, it doesn't want to, but it will as long as all of the other elements are perfect with their 8. All right, I would like you to pause the video and try this one on your own. And the answer is going to come up in 3, 2, 1. All right, here's my structure. So the first thing I did was add up my valence, 7 each from the fluorine. And there's 3 of those, 7 from the bromine, so 28 total. I then arranged the element Br in the middle because there's just 1 of him and the 3 fluorines. Then I did single bonds, and that used up 6 electrons in my piggy bank, so I had 22. Fill the outer. So each fluorine had 2 from the bond, but needed 2, 4, 6 more in the form of lonely pairs. So this fluorine has 1 bond and 3 lone pairs. This guy has 1 bond and 3 lone pairs. 1 bond and 3 lone pairs. So that used up 18. So I had 4 left. And now we fill the middle. This bromine in the middle only wants 2 because he has 2 in this bond, 2 here. So 2, 4, 6. He only wants 2 more, but there's 4 left in my piggy bank. And remember, if there's extra, we'll put those on the center atom. So bromine has 2, 4, 6, 8, 10, 2 lone pairs and 3 bonds, but that made my piggy bank down to 0. Is bromine in the 3rd row of my periodic table or lower? Yes, he is. So he is allowed to have an expanded octet as long as his buddies are perfect with 8, which that's the case. Okay, the last thing I want to talk about is the multiple bonds. So we saw one example with a double bond. And just a reminder, this is the last resort only if our piggy bank is at 0 and the element in the center is not satisfied, meaning it doesn't have 8 electrons. Okay, so a double bond is when 2 atoms share 2 pairs of electrons. So this is a double bond right here. There are 2 4 electrons in those bonds. Okay, this is another double bond. There's 2 4 in those bonds. So this carbon in the middle feels like it has 8 electrons, 2, 4, 6, 8, 2 in each of those bonds. Okay, a triple bond is when 2 atoms share 3 pairs of electrons. So 2, 4, 6 electrons are being shared between those nitrogens. This is a diatomic covalent bond, right? Nitrogen bonded to nitrogen. I say diatomic because they're both nitrogen. Okay, so again, please don't go crazy with the multiple bonds. It's a last resort if your piggy bank is at 0 and your middle element does not have all 8. Then we do double bonds or triple bonds. Okay, we will do lots and lots of practice with this in class, but hopefully this gives you something to think about. And again, we'll do tons of practice until these feel super easy. Have a great rest of your day.